All physics before the 20th century are called classical physics. And one of the branches of classical physics is classical mechanics, which is the study of the motions of macroscopic particles or objects. Welcome to my advanced physics class. In this channel, we discuss modern physics and classical physics. Kindly subscribe, click on the notification bell, share, comment, and like my videos. In physics, a law is a brief statement that summarizes a fact of nature. So if an observer of nature observes a repeated fact, something which is true, and then decides to put it down in a very short statement, summarizing the whole fact, that is called a law. And there are countless of them in physics. We have Faraday's law, we have law of flotation, Lenz's law, we have Newton's laws of motion, which happens to be our discussion for this episode. 300 years ago, Isaac Newton discovered these three laws, which are the backbone of classical mechanics. First of his laws is dubbed the law of inertia. This law states that an object at rest, that is relative to you, or an object in a constant velocity in a straight line, still relative to you, will continue to be in that state until an external force acts on that object. So in his book, Principia Mathematica, he put it down this way, that an object at rest will continue to stay at rest, and an object in uniform motion in a right line will continue to be in that state unless or until an external force acts on the object. This law was even prior to Newton himself. It dates back to the times of Aristotle and Galileo. They also discovered the same situation. But then Newton added something later by saying that you don't even need an external force to cause an object to move. So uniform motion, according to Isaac Newton, is for free. In empty space, if an object is coursing at a constant velocity, it continues forever unless an external force acts on it. And the reason why, in our perspective, things have come to rest, stones, rocks, trees, etc. have come to rest, is the fact that external forces are acting on them. These external forces could be friction, could be drag forces, could be air resistance, and many more. So in the absence of these external forces, every object will start coursing at a constant velocity in a right line. The property that gives an object the law of inertia is called the mass. And an object mass is the resistance to any external force. This law has several applications. There are many phenomena in nature which can be explained or interpreted by the law of inertia. Say you are in a car coursing at a constant velocity, and all of a sudden the driver applies a brake. All the passengers jerk forward in response to that braking system, indicating that initially you were at a constant velocity and you want to move at that same constant velocity, even though there is an external force. So the object has mass and would like to resist that braking system by jerking forward. If a car also negotiates or bends a curve, passengers tilt outward, indicating they want to still maintain that constant velocity. There are several others, but let's keep these two. The second of Newton's laws is an equation that says F in vector form is equal to ma. Arguably, this is the most important equation in the whole of physics. And all other mechanical phenomena can be explained according to this law. F is equal to ma, which says that a net force on an object in a system is equal to that object's inertia, which is the mass, times the object's acceleration, which is the change in velocity. The F, which is the force, is the cause of the object's motion. The A is the effect on the object. So the law says that if a net force, which is a cause for an object to move, exerts on an object, it gives the object an effect, which is the change in velocity. And without a net force, there is no change in velocity. And the distinguishing factor that says that different objects will experience different effects under the influence of the same force is the mass or the masses of those objects. The higher your mass, the lesser you respond to the effect of the mass, the effect of the force. And the less your mass, the more you respond to the effect of the force. At the first glance at this law, you might think it is very simple and understandable. Yes, it is, but it is very subtle. Over the years, I have realized that you don't say the force on an object is ma. The force on an object is not ma. It is a separate entity. In fact, it is the job of physicists to discover forces of nature. And after you are done with that, you equate to ma, which is a general law, and see the evolution of the particle in that system. So the force on an object is due to a spring, due to gravity, due to friction, due to tension, due to electromagnetic forces, etc. And after you are done unraveling at those forces of nature, then you can equate to ma and see the behavior of the object in that system. That is the subtlety of this law. So Robert Hooke discovered that if you have an elastic spring, say on a frictionless surface, and you pull it from its rest length that I call x equal to 0, you can pull it to say any x position. Then there are forces in the spring called the spring force. If you pull to the right, the force of the spring is to the left, which tries to pull the object back to its original or equilibrium position. Let me call that force F. And Hooke experimented with the spring for a long time, conducted several experiments, and came up with a discovery that the force exerted by the spring is proportional to how much you pull it. That is x. Then if you introduce a proportionality constant, then you have F is equal to kx. And the vector form of the force is equal to negative kx. This one just indicates that if you pull to the right, the force is to the left. That's why you have a negative sign here. So Hooke triumphed for this discovery. You ask yourself, what is the difference between F is equal to negative kx and F is equal to ma? The difference is F is equal to negative kx. It's a specific force only for springs. And F is equal to ma is a general force law that links the net force to inertia to the effect on that object, which is the acceleration. So So if you are done with negative kx, equate to ma and see how the system will behave. So negative kx is equal to ma. In other words, mx double dot, where x double dot is a second derivative of the position x, which is the acceleration, is equal to negative kx. X double dot would therefore be equal to negative k over m times x. This is called a differential equation. A differential equation is an equation of a function in terms of its derivative. So the behavior of this object under the spring and mass system would behave according to this differential equation. So if you are a physicist and you cannot solve this differential equation, then you forward it to the mathematicians. Then they will tell you that this one says that you need a function whose second derivative is equal to negative a constant times the function itself. And that function is a trig function, a cost function, so to speak. And if you get that cost function and study or read the physics into it, you would come to know that this object will behave in a periodic fashion that we call a simple harmonic oscillator. It will oscillate back and forth under the influence of this spring force. We will study this equation later on. But this is an example just to tell you F is equal to ma. It's not the force on an object. The force on an object is due to, say, a spring, gravity, etc. So Isaac Newton also discovered the law of gravitation. And he discovered that the strength of gravitational pull is equal to gravitational constant times the product of the two masses under the system divided by the distance between their centers squared. So then if you discover this law, equate to ma and see the behavior of the object. So then you say ma is equal to gmm over r squared. This is just the strength of the force, and in vector form it will be negative. So in vector form, let me introduce a negative that way. So then m times a, and a is a second derivative of the position function r. So let me call that r dot dot is equal to negative g mm divided by r squared. And if you're able to solve this differential equation, then you know how an object will behave in the vicinity of a massive object exerting a gravitational pull on it. And Newton solved that and saw that objects will move in an elliptical fashion. This equation also applies to objects very close to the surface of the earth. And for that one, ma will be equal to negative g capital M, which stands for the mass of the earth, times the mass of that object divided by, because the object is very close to the surface of the earth, that is, if this is the earth and this is the object, the distance between their centers can be approximated to be the radius of the earth, since the external distance is negligible. So divided by the radius of the earth squared. And it turns out that this mass of the object cancels this mass of the same object, even though the properties are different. This stands for the resistance of the object to gravity, or the inertia of the object. And then this stands for gravitational mass, how much it wants to accelerate towards the earth. But they cancel. And you get A to be equal to negative G capital M divided by R squared. And all these quantities here are constant. The gravitational constant, mass of the earth is a constant, radius of the earth is a constant. So then it tells you the acceleration of every object very close to the surface of the earth is a constant regardless of your mass. And we've given it a g, which is equal to negative g capital M over R squared. And if you put in the values, it's approximately 9.8 meters per second squared. The negative sign indicates it is pointing downwards. So all that a physicist needs to do, or needs to work out, or find out, or discover are the forces of nature. If you're able to do that, then hooray, equate to MA, and you become tipped for a Nobel Prize. So let's keep searching for forces of nature. That is for the second law, arguably the most important law in the whole of physics. Newton's third law says that, Newton's third law of motion says that to every action, there is equal but opposite reaction. So in simplistic terms, action is equal to negative reaction. If you exert a force on an object, the object also exerts equal but opposite force on you. And this phenomena, this law has several phenomena that can be explained. For instance, if you are on a frictionless or icy surface and you throw an object in this direction, there is a force in this direction. The object will exert equal force on you, so you slip backwards. If you are in a canoe, then you are holding your paddle. As you paddle to the back, or if you paddle backwards, or if you push on the water will push on you, and you and the whole canoe move forward. If you have a balloon and you inflate it, as the air molecules gush out in this direction, the balloon also moves in this opposite direction. Rockets also function using the third law of motion, according to Newton. Now, this law can be shown, though cannot be proved. And that sends me back to the second law. This law cannot be proved from first principles, or it is a law. There is no way you can prove this from first principles. It is a law that states that force is equal to MA, and it is a fact. So you explain phenomena according to it. But let's show the third law, that if you have two objects which are connected objects on a frictionless surface, and say you apply a force of 10 newtons. Now, how do you know you're applying a force of 10 newtons? Now, it may be due to a spring. If you have a spring with a force constant, say 1, this is the force of a spring. So if the spring constant is say 1, and you pull the spring 10 meters, it means you are exerting 10 newtons of force. How do you know you have 1 kilogram? That one is conventional. Scientists would have to pick one object and say this is 1 kilogram, and all other masses will be measured relative to it. How do you know an object is moving with this acceleration? That can be measured by using meter rules, tape measures, and clocks. All you need is 3 position measurements. The first 2 will be for the first velocity, the second 2 will be for the second velocity. And that change in velocity, within that change in time, delta t, will give you the A. So we just have to know these symbols are not just mathematical symbols, but it can be measured and can be worked with. Well, so let's return to this. You exert a 10 Newton force on this connected object. And let's say the bigger one has a mass of 3 kilograms, the smaller one with a mass of 2 kilograms. So under the influence of this 10 Newton force, F is equal to ma. That tells you this is one dimension. 10 newtons will be equal to the two masses because they are connected. 5 times A. And A will give you 2 meters per second squared. So these two objects will change their velocity every 1 second by 2 meters per second. If they were initially at rest, within 1 second, they will be moving at 2 meters per second squared. In the next second, they will be moving with 4 meters per second squared. 4 meters per second. In the next, 6 meters per second. So then let's isolate the first object. Let's call it A and then call this B. If we do that, for object A, which is a 3 kilogram mass, it is under the influence of the 10 Newton force. And then again, as object A pushes on B, B also pushes back at it. So let's just say the force B exerts on A is FB on A. So they are in contact. A pushes on B, B pushes on A, according to the third law. This is called a free body diagram. And by studying this, the force 10 minus FBA, since it is pointed in the opposite direction, is equal to the mass 3 times the acceleration, which is 2. So FBA, the force of B on A, will be equal to 4 newtons. So object B will push back at object A with the force of 4 newtons. Let's see which force object A also exerts on B. So let's isolate object B, which is a 2 kilogram mass. And the only force on B is a force A is exerting on it. You don't include this 10. Because for all you know, 10 is rather pushing on A. And A is pushing on B. So in a free body diagram, the only force you know on an object is a force one object is pushing on it or pulling on it. So we call that force A exert on B as FAB. And that is all. And it tells you FAB is equal to the mass 2 times the acceleration, which is 2. And that is equal to 4 newtons. So as we can see, FBA is 4 newtons, FAB is 4 newtons. And both of them pushes on each other with the same 4 newtons, except that the directions are opposite. Look at FBA. FBA is to the left, but FAB is to the right, telling us that FBA is equal to the negative of FAB. So to every action, there is equal but opposite reaction. If you shoot with a gun, the gun pushes on the bullet pushes on the gun and you. So you feel the recoil of the gun. So you need to stand firm so not to fall. And that explains why people also need seat belts in cars, in order not to be thrown out of a windscreen. Now let's show the third law with another example. And here there's a presence of a third force called the tensional force. So there are 3 objects here. We have block A, block B, then we have a string. And this string happens to be massless, approximately massless. So here they are connected by a string under the influence of the 10 Newton force. And that tells you the 10 Newton force will pull them together at a constant acceleration. So that will be equal to their total mass, which is 5 times the acceleration A. And A is still 2 meters per second squared. Now let's isolate object A. And if you do that, you have the object A, 3 kg. What is the force on A? The force on A is a force the string is pulling it. So the string is pulling it. Let's call that T, standing for tension. You don't include the 10 Newton force. Now the 10 is also pulling A. No, you don't know that. 10 is pulling B, and B is pulling the string, and the string is pulling A. That's all we know in the free body diagram. Then let's draw the string. That's the second body. So the string pulls on object A, the object A pulls on the string to the left. So the string also experiences a force to the left, which is equal to the force the string pulls object A. And then again, the string pulls on B. See, so object B pulls on the string also pulls object B. So object B pulls the string also in this direction with the same tension. Now this is what we call tensional force. Tensional force is a force tensional forces are forces which are equal in magnitude but opposite in direction, stretching a body out. So if one person holds my right and the other holds my left and pulls me in a way to stretch me out, those forces are called tensional forces. They are equal and opposite, but it doesn't mean they can't do any work. They can. They can tear the body apart. And the third body is B, of course. So B is 2 kilograms. The string will pull B in this direction, the T, and 10 Newton force also in this direction. So for object A, we have T is equal to the mass 3 times the acceleration 2. And that tells you T is equal to 6 newtons. Before we come to the string itself, let's visit object B. And object B says 10 minus T is equal to the mass 2 times the acceleration 2. So if 10 minus T is equal to 4, then T is equal to 6 newtons. And look at this T is pulling to the left, and this T is pulling to the right, but they have equal magnitudes, but they are in the opposite direction, one to the left, one to the right, showing Newton's third law. And now to the string itself, there is no net force on this string because T minus T is 0. So 0 is equal to ma, and A is equal to 0 over m, and that is equal to 0. The object will have 0 acceleration. And then again, the object, the string, has to be massless. It has to be massless because if it is not massless, and say it has a little net force on it, that say now these two do not cancel and you have a net tension, say 2, that will be equal to ma. And now if the object is massless, you put 0 here, then A would of course be an infinity. So I just wanted to say the object shouldn't have any net force on it. The string would have a net tension of 0, and it should be so given that the object is massless. If you have a net tension divided by 0 will give you an infinite acceleration, and the string will break. But the whole equation will break. So given that there is no net tension on it, which is 0, is equal to, now it is also massless, so mass is equal to 0 times A. So you have A is equal to 0 over 0. Now 0 over 0 can have so many values, can take any value. And in this physical case, it is equal to 0 and not equal to infinity. So by the way, we've shown Newton's third law too. Once again, this is my advanced physics class. Kindly subscribe, share, comment, click on the notification bell, like my videos. let's watch out for the next episode, which happens to be the applications of the second Newton's law of motion, F is equal to ma, arguably the most important law in the whole of classical mechanics. Stay tuned.